The facility sits beneath the border between France and Switzerland, a ring of superconducting magnets 17 miles in circumference, buried more than 500 feet below the surface of the Earth. From above, the landscape reveals nothing. Farmland, villages, the ordinary geometry of human life, continuing as it has for centuries. But below, in tunnels carved through ancient rock, particles are accelerated to velocities so close to the speed of light that the difference becomes a question of decimal places extending into territories where language begins to fail. This is the Large Hadron Collider, and in recent months, something unexpected has emerged from the data streams flowing out of its detectors, something that does not fit into frameworks we have spent more than a century constructing, testing, and refining. Before we go further, if you're watching on a smaller screen, consider expanding to full view, and if this subject matter resonates with you, subscribing ensures you won't miss what comes next. What has been found is not a simple anomaly, not a statistical fluctuation that will dissolve with more data, but a persistent, reproducible signature that suggests the architectural reality at its most fundamental level may contain features we never anticipated, features that, if confirmed, would require us to reconsider not merely one theory or one set of equations, but the entire edifice of our understanding of what exists, how it behaves, and why the universe possesses a specific character it does rather than some other configuration among infinite possibilities. To understand what has been detected, we must first establish what was expected. The standard model of particle physics represents one of the most successful scientific achievements in human history. It is a mathematical framework describing 3 of the 4 fundamental forces, cataloging the elementary particles that constitute matter and mediate interactions, and predicting the outcomes of high-energy collisions with precision that, in some cases, extends to 10 decimal places. When the Higgs boson was discovered in 2012, it completed the particle content of this model, filling the last gap in a structure that had been under construction since the mid-20th century. The discovery was celebrated not merely because a new particle had been found, but because its properties matched predictions made decades earlier with extraordinary accuracy. The mass, the decay channels, the production rates, all aligned with what the equations demanded. This alignment was both triumph and closure, the sense that a chapter had ended, that the map of the subatomic world was complete within the energy ranges accessible to current technology. But the standard model, for all its predictive power, has always been understood as incomplete. It does not incorporate gravity. It offers no explanation for the existence of dark matter, which comprises approximately 85% of the matter content of the universe, yet interacts with ordinary matter only through gravitational effects. It provides no account of the asymmetry between matter and antimatter that allowed matter to persist after the Big Bang, rather than annihilating completely. It contains parameters, numerical values that must be measured rather than derived, whose specific magnitudes appear arbitrary, fine-tuned to a degree that seems to demand explanation. And it remains silent on questions that touch the deepest conceptual foundations of physics. Why does the universe obey quantum mechanical rules? Why does time flow in one direction? Why do we observe 3 spatial dimensions rather than 2 or 7 or some other number? These are not questions the standard model was designed to answer, but they are questions that any truly fundamental theory must eventually confront. For decades, physicists have constructed extensions to the standard model, theoretical architectures that attempt to address one or more of these gaps. Supersymmetry proposes that every known particle has a heavier partner, doubling the particle content and offering a potential explanation for dark matter, while also stabilizing certain calculations that otherwise yield nonsensical infinities. Extra dimensions, compactified into shapes too small to detect directly, appear in string theory and related approaches, providing mechanisms by which gravity might be unified with the other forces. Grand unified theory suggests that the electromagnetic, weak, and strong forces merge into a single force at extremely high energies, implying a deeper symmetry broken by the cooling of a universe. Each of these frameworks makes predictions, signatures that should appear in the data if the theory correctly describes nature. And for decades, those signatures have not appeared. Supersymmetric particles have not been found. Extra dimensions have not revealed themselves. The predicted unification energy scales remain beyond experimental reach, and the indirect consequences that should ripple down to accessible energies have not materialized. This absence has led to a period of tension in fundamental physics. The theoretical structures are mathematically elegant, internally consistent, and conceptually compelling, yet nature seems indifferent to them. Some researchers have begun to question whether criteria guiding theory construction, beauty, symmetry, mathematical simplicity, are reliable guides to truth, or whether they reflect human aesthetic preferences that nature is under no obligation to satisfy. Others have argued for patience, noting that the energy scales required to test many of these ideas directly are far beyond current capabilities, and that the absence of evidence is not evidence of absence. Still others have suggested that the standard model, rather than being a provisional sketch awaiting completion, might be closer to a final answer than anyone expected, with the remaining mysteries residing not in new particles or forces, but in the initial conditions of the universe or the interpretation of quantum mechanics itself. Into this landscape of uncertainty, the new data from CERN has arrived. The anomaly first appeared in the decay patterns of particles produced in proton-proton collisions at energies of 13 teraelectronvolts, conditions that recreate, in miniature, the thermal environment of the universe a trillionth of a second after the Big Bang. The detectors at CERN are layered instruments, surrounding the collision point with concentric shells of sensors designed to track particles as they emerge from the interaction, measuring their energies, momenta, and trajectories with precision. When particles decay, transforming into other particles in accordance with quantum mechanical probabilities, the distribution of those decay products carries information about the underlying process. The standard model predicts these distributions with great specificity. It specifies not only which decay channels are allowed, but the relative rates at which they should occur, the angular correlations between decay products, the energy spectra that should be observed. What the detectors recorded was a subtle excess, a slight elevation in the rate of certain decay events involving bottom quarks and tau leptons, particles that are themselves unstable and short-lived, existing for mere fractions of a second before decaying into lighter particles. The excess was not large, approximately 3 to 4 standard deviations above the expected background, a level that in isolation would warrant further investigation, but not immediate claims of discovery. In particle physics, the threshold for claiming a discovery is typically set at 5 standard deviations, corresponding to a probability of less than 1 in 3.5 million, that the signal is a statistical fluctuation. 3 to 4 standard deviations represent probability of roughly 1 in several thousand, significant but not definitive. However, this excess was not isolated. It appeared consistently across multiple decay channels, in different datasets collected over several years, and in independent analyses conducted by separate teams using different statistical methods. The consistency of the signal across these diverse contexts elevated its significance beyond what the raw statistical measure would suggest. Moreover, the pattern of the excess did not match any of the signatures predicted by the popular extensions to the standard model. It was not consistent with supersymmetry, which would have produced different particle combinations and energy distributions. It was not consistent with the existence of heavy resonances, new particles that decay into the observed final states, because the mass spectrum did not show the characteristic peaks that such resonances would create. It was not consistent with extra dimensions, which would have altered the overall rate of production without preferentially affecting specific decay channels. Instead, the pattern suggested something more subtle, a modification not in the particle content of the theory, but in the relationships between existing particles, in the coupling constants that determine the strength of their interactions, or in the structure of the vacuum state itself. The vacuum, in quantum field theory, is not empty. It is a seething, fluctuating medium, filled with virtual particles that momentarily appear and disappear in accordance with Heisenberg's uncertainty principle. These fluctuations are not merely theoretical constructs. They have measurable effects, contributing to the masses of particles, altering the strength of forces at different energy scales, and even producing observable phenomena like the Casimir effect, where two metal plates placed very close together experience an attractive force due to the suppression of certain vacuum fluctuations between them. The properties of the vacuum are determined by the fields that permeate it and by the interactions between those fields. In the standard model, the vacuum is assumed to be stable or at least metastable, existing in a configuration that represents a local minimum of energy. But there is no fundamental principle that guarantees this. It is possible, Indeed, some calculations suggest it is probable that the vacuum we inhabit is not the true ground state of the universe, but false vacuum, a temporary configuration that could, under the right conditions, tunnel into a lower energy state, triggering a transformation that would propagate at the speed of light, rewriting the laws of physics in its wake. The anomaly at CERN has led some theorists to propose that what is being observed is not a new particle, but evidence of structure within the vacuum itself, a signal that the vacuum is not uniform, that it contains defects or domains or fluctuations on scales that are just beginning to become accessible to experiment. This is a radical suggestion, because it implies that the constant we measure, the masses of particles, the strengths of forces, the value of the cosmological constant, might not be truly constant, but could vary depending on the local properties of the vacuum. Such variation would not be detectable in most circumstances, because the domains would be vast compared to subatomic scales, and any variations would average out over the volumes accessible to measurement. But in the extreme conditions created inside the Large Hadron Collider, where energy densities approach those of the early universe, it is possible that the vacuum is being probed in ways that reveal its hidden structure. To explore this possibility, we must consider the concept of symmetry breaking. In physics, symmetry refers to a situation where the laws governing a system remain unchanged under certain transformations. Rotational symmetry means that the laws of physics are the same regardless of which direction you face. Translational symmetry means they are the same regardless of where you are located. Gauge symmetries, which are central to the Standard Model, are more abstract, involving transformations in internal spaces associated with the fundamental forces. The electromagnetic force, for example, is associated with a symmetry known as U1, while the weak force is associated with a symmetry called SU2, and the strong force with SU3. These symmetries dictate the form of the interactions, the number of force carriers, and the relationships between coupling constants. However, these symmetries are not manifest in the observed world. If they were, all particles would be massless, and the forces would all have infinite range. The fact that particles have mass and that forces have different ranges indicates that the symmetries are broken. This breaking is not a violation of the underlying laws, but a consequence of the state of the system. The laws themselves retain the symmetry, but the vacuum does not. This is analogous to a ferromagnet. The underlying laws of electromagnetism possess rotational symmetry, treating all directions equivalently. But when a ferromagnet cools below its critical temperature, it spontaneously magnetizes in one particular direction, breaking the rotational symmetry. The choice of direction is arbitrary, determined by microscopic fluctuations, but once made, it defines a preferred axis. In the Standard Model, symmetry breaking is accomplished by the Higgs field. This field permeates all of space, and its non-zero value in the vacuum breaks the electroweak symmetry, giving mass to the W and Z bosons that carry the weak force, and to the fermions, the matter particles. The discovery of the Higgs boson confirmed that this mechanism is realized in nature. But the Higgs field itself raises questions. Why does it have a non-zero value in the vacuum? Why does that value have the specific magnitude it does? The potential energy function of the Higgs field, which determines its behavior, is shaped like a Mexican hat, with a central peak and a circular trough. The vacuum sits not at the peak, but in the trough, at a specific radius from the center. But the choice of radius, the specific value of the Higgs field, is not explained by the Standard Model. It is an input, a parameter that must be measured. The anomaly at CERN might be suggesting that the Higgs sector is more complex than the minimal version incorporated into the Standard Model. Perhaps there are additional Higgs fields, or perhaps the Higgs potential has features not captured by the simple Mexican hat shape. Extensions involving multiple Higgs doublets have been proposed for decades, motivated by various theoretical considerations. In such models, there are additional scalar particles, some electrically neutral, some charged, with masses that could range from accessible energies up to scales far beyond current reach. These additional particles would modify the decay rates and production cross-sections of the known Higgs boson, and they could produce the kinds of anomalies now being observed at their masses and couplings fall within certain ranges. But there is another possibility, one that is more radical and more troubling. The anomaly might be indicating that the vacuum is unstable, not in the sense that it will imminently decay, but in the sense that it is closer to a phase boundary than we realized. The calculations of vacuum stability in the Standard Model depend sensitively on the precise values of the top quark mass and the Higgs boson mass. With the measured values, the Higgs potential develops a second minimum at extremely high field values, around 10 to the 16 gigaelectron volts, an energy scale associated with the unification of forces. This second minimum is deeper than the one we inhabit, meaning that it represents a lower energy state. However, the barrier separating the two minima is high enough that the tunneling probability is vanishingly small over timescales comparable to the age of the universe. In this sense, the vacuum is metastable, technically unstable but practically eternal. However, these calculations assume that there is no new physics between the electroweak scale and the Planck scale, the energy scale at which quantum gravitational effects become important. If there are new particles or interactions in this vast desert of energy, they could alter the shape of the Higgs potential, raising or lowering the barrier, shifting the position of the minima, changing the tunneling rate. The anomaly at CERN might be an early hint of such new physics, a signal that the vacuum is closer to criticality than the minimal Standard Model suggests. If this is the case, it would have profound implications not only for particle physics, but for cosmology, because vacuum stability is intimately connected to the history and fate of the universe. In the early universe, when temperatures were extremely high, the Higgs field was not stuck in the trough of its potential, but was fluctuating wildly, exploring a full landscape of possible values. As the universe cooled, the field underwent a phase transition, settling into the trough, breaking the electroweak symmetry. This transition was not instantaneous. It occurred through the nucleation of bubbles, regions where the Higgs field had settled into the trough, expanding into regions where it had not. The dynamics of this process, the rate at which bubbles formed, the speed at which they expanded, the way they collided and merged, all depend on the detailed shape of the Higgs potential. If the potential has features not captured by the minimal model, the phase transition could have proceeded differently, leaving imprints on the distribution of matter and energy in the universe, imprints that might still be detectable today in the cosmic microwave background or in the large-scale structure of galaxies. Furthermore, if the vacuum is closer to a phase boundary than expected, it raises the possibility that certain high-energy events, such as the collisions produced at CERN, could nucleate a bubble of true vacuum, initiating a transition that would propagate outward, converting the false vacuum into the true vacuum, annihilating everything in its path. This is not a new concern. It was raised in the 1990s before the relativistic heavy ion collider was turned on, and again before the Large Hadron Collider began operations. In both cases, detailed analyses concluded that the risk was negligible, because cosmic rays routinely produce collisions at far higher energies than any accelerator can achieve, and the universe has not yet undergone such a transition. The fact that we exist is evidence that these processes are safe. However, the new anomaly introduces a nuance. If the vacuum is not uniform, if it contains domains or defects, then the conditions inside an accelerator might not be exactly analogous to those produced by cosmic ray collisions. The geometry matters. The energy density matters. The duration of the interaction matters. It is possible, though highly speculative, that collider experiments probe a vacuum in ways that natural processes do not, and that the anomaly is a warning sign of something deeper and more dangerous. But let us not get ahead of ourselves. The anomaly has not been conclusively established. It has not reached the 5 sigma threshold. It could still be a statistical fluctuation or a systematic error, or an artifact of the analysis method. The detectors at CERN are extraordinarily complex instruments, containing millions of individual sensors, each of which must be calibrated and understood. The data analysis involves reconstructing particle trajectories from patterns of signals, disentangling overlapping events, correcting for detector inefficiencies and backgrounds, and applying statistical techniques to extract signals from noise. At every stage, there are opportunities for subtle biases to creep in, for assumptions to skew results, for correlations to be misinterpreted. The collaborations working on the ATLAS and CMS detectors are aware of these dangers and employ rigorous procedures to guard against them. But the history of particle physics is littered with anomalies that seemed significant at the time but evaporated with more data or improved analysis. Nevertheless, the anomaly has generated intense interest because it appears in a sector of the Standard Model that is particularly sensitive to new physics. The couplings of the Higgs boson to fermions, the matter particles, are proportional to the fermion masses. This means that the Higgs couples most strongly to the heaviest fermions, the top quark, the bottom quark, and the tau lepton. Any modification to the Higgs sector, any additional fields or interactions, would first manifest in the decays involving these heavy particles. The fact that the anomaly involves bottom quarks and tau leptons is therefore not surprising. It is exactly where one would expect to see deviations if the Higgs sector is more complex than the minimal model. Moreover, the anomaly appears at energy scales that are accessible to current technology but were not thoroughly explored by previous experiments. The Large Electron-Positron Collider, which operated at CERN from 1989 to 2000, studied electron-positron collisions at energies up to about 200 gigaelectronvolts, probing properties of the Z boson and searching for the Higgs. The Tevatron, which operated at Fermilab from 1983 to 2011, collided protons and antiprotons at energies up to 2 teraelectronvolts, discovering the top quark and searching for the Higgs at higher masses. The Large Hadron Collider, with collision energies of 13 teraelectronvolts and eventually 14, extends the reach significantly, producing particles and interactions that were too rare or too energetically inaccessible for previous machines. The anomaly sits in this newly accessible territory, a regime where the standard model has been tested, but not exhaustively. To understand why this matters, consider the concept of effective field theory. The standard model itself is an effective field theory, a description that is valid within a certain range of energies, but is not expected to hold at arbitrarily high energies. At low energies below the masses of the W and Z bosons, the weak force can be described by an effective interaction, the Fermi theory of beta decay, which treats the interaction as point-like, occurring at a single location in space and time. This description works well for low-energy processes, but breaks down at higher energies, where the finite range of the weak force becomes important and the W and Z bosons must be included explicitly. Similarly, the standard model as a whole is expected to break down at some high energy, giving way to a more fundamental theory that includes gravity and possibly other new features. The art of effective field theory lies in understanding how the details of the high-energy theory manifest themselves in the low-energy world. Even if the high-energy particles are too heavy to be produced directly, their effects can appear indirectly through virtual processes, quantum fluctuations in which the heavy particles briefly appear before disappearing. These virtual processes modify the predictions of the low-energy theory in calculable ways. By measuring deviations from the low-energy predictions, one can infer properties of the high-energy theory without accessing those energies directly. This is the principle underlying precision measurements in particle physics. By measuring quantities with extreme accuracy and comparing them to standard model predictions, physicists can search for tiny deviations that signal the presence of new physics. The anomaly at CERN could be such a deviation. If the excess in bottom quark and tau lepton decays is real, it suggests that there are additional contributions to these processes beyond what the standard model predicts, contributions from virtual particles or interactions that we have not yet identified. The challenge is to determine what those contributions are, to construct a model that accounts for the anomaly while remaining consistent with all other measurements, of which there are thousands, each constraining the possibilities in different ways. This is a formidable task. The space of possible models is vast, and many models that explain one anomaly create tensions with other measurements. The process of model building is therefore iterative and collaborative, with theorists proposing models, experimentalists testing their predictions, and the cycle repeating as the data accumulates. In the months since the anomaly was first reported, dozens of papers have appeared, proposing interpretations ranging from the conservative to the exotic. Some invoke additional Higgs bosons, as mentioned earlier, with carefully chosen masses, and couplings designed to enhance the problematic decay channels without affecting others. Some propose new vector bosons, heavy particles similar to the photon or the Z boson, but with different quantum numbers, which would be produced in the collisions and then decay into bottom quarks and tau leptons. Some suggest that the anomaly is related to dark matter, that the particles being produced are not fully within the standard model but are portals to a hidden sector, a collection of particles and forces that interact with ordinary matter only weakly. Some go further, proposing that the anomaly is evidence of quantum gravitational effects leaking into the low-energy world, that the collision energies at CERN are high enough to probe the structure of space-time itself at scales where quantum mechanics and general relativity begin to overlap. This last possibility is particularly intriguing because it touches on one of the deepest problems in theoretical physics, the incompatibility between quantum mechanics and general relativity. Quantum mechanics describes the behavior of matter and energy at the smallest scales, treating particles as wave functions, probabilistic entities that exist in superpositions of states until measured. General relativity describes gravity as the curvature of space-time, a geometric property determined by the distribution of mass and energy. These two frameworks have been extraordinarily successful within their respective domains, but they are fundamentally incompatible. General relativity assumes a smooth, continuous space-time, a background on which events occur. Quantum mechanics, particularly in its modern formulation as quantum field theory, treats fields as fundamental entities, with space-time as a stage on which the fields evolve. When one attempts to apply quantum mechanics to gravity, treating the gravitational field as a quantum field on the same footing as the electromagnetic or weak fields, the resulting theory is non-renormalizable. It produces infinite answers to finite questions, infinities that cannot be absorbed into redefinitions of parameters as they can in other quantum field theories. String theory and loop quantum gravity are two of the most developed approaches to resolving this incompatibility, but neither has yet made contact with experiment in a way that allows definitive testing. String theory posits that the fundamental constituents of nature are not point-like particles, but one-dimensional extended objects, strings, whose different vibrational modes correspond to different particles. In this framework, gravity arises naturally as one of the vibrational modes, and the theory is finite, free of the infinities that plague quantum field theory approaches to gravity. However, string theory requires extra dimensions of space, typically 6 or 7, which must be compactified into shapes so small that they have not been detected. The specific shape of these extra dimensions determines the properties of the particles and forces in the observable four-dimensional world, and there are an enormous number of possible shapes, leading to a landscape of possible universes, each with different laws of physics. This abundance of possibilities is seen by some as a strength, allowing for the fine-tuning of constants to match observations, and by others as a weakness, rendering the theory unpredictive. Loop quantum gravity, on the other hand, does not require extra dimensions or strings. It attempts to quantize spacetime itself, treating it not as a smooth continuum, but as a discrete structure, a network of loops and nodes at the Planck scale, the incredibly tiny length scale of about 10 to minus 35 meters, where quantum gravitational effects are expected to dominate. In this picture, spacetime is granular, with a minimum measurable length and a minimum measurable time. This granularity eliminates the infinities of quantum field theory, but at the cost of giving up the smooth background that general relativity assumes. The challenge for loop quantum gravity is to show that the smooth, continuous spacetime of our everyday experience emerges as an approximation when one averages over many Planck scale quanta, and to make predictions that can be tested. The anomaly at CERN does not directly test string theory or loop quantum gravity, because the Planck scale is far beyond the reach of any conceivable accelerator. But if quantum gravitational effects modify the behavior of particles at lower energies, even slightly, those modifications could be detectable. Some models suggest that the granularity of spacetime introduces a tiny amount of noise into quantum processes, a randomness that is not present in standard quantum field theory. Other models propose that the extra dimensions of string theory, though compactified, leave imprints in the form of Kaluza-Klein states, heavy particles that are excitations of the extra dimensions, which should be produced in high-energy collisions if their masses are not too large. Still others suggest that the vacuum energy, the cosmological constant, is related to the dynamics of the extra dimensions, and that measuring properties of the Higgs field provides indirect information about those dynamics. The cosmological constant is itself one of the most perplexing problems in physics. It represents the energy density of empty space, a contribution to the curvature of the universe that causes the expansion of the universe to accelerate. Observations of distant supernovae in the late 1990s revealed this acceleration, leading to the inference that the cosmological constant is positive but extraordinarily small, about 120 orders of magnitude smaller than the value that naive quantum field theory calculations predict. This discrepancy, known as the cosmological constant problem, is one of the largest failures of theoretical physics. The vacuum energy should receive contributions from all the quantum fields that permeate space, and when one adds up these contributions, one obtains a result that is catastrophically large. If the cosmological constant were as large as this calculation suggests, the universe would have either collapsed immediately or expanded so rapidly that no structures could form. The fact that we exist implies that some mechanism, unknown and unexplained, cancels almost all of this vacuum energy, leaving behind the tiny residue that we observe. The Higgs field contributes to the vacuum energy. Its non-zero value in a vacuum represents a certain energy density, which should gravitate, affecting the expansion of a universe. Yet when one calculates this contribution, it too is enormous compared to the observed cosmological constant. The fact that the observed value is so much smaller implies that there must be additional contributions from other fields or from some deeper principle that cancel the Higgs contribution to extraordinary precision. This cancellation is not explained by the Standard Model, nor by any of its proposed extensions. It is a mystery that points toward missing physics, either at very high energies, near the Planck scale, or in initial conditions of the universe, or in the interpretation of quantum mechanics itself. Some theorists have proposed that the solution to the cosmological constant problem lies in the multiverse, the idea that our universe is just one of an enormous, possibly infinite number of universes, each with different values of the physical constants. In this picture, the cosmological constant is not explained but is selected by anthropic reasoning. Universes with cosmological constant that is too large do not form galaxies, stars, or planets, and therefore do not produce observers. We find ourselves in a universe where the cosmological constant is small, because only in such universes can observers exist to make measurements. This explanation is controversial, because it abandons the goal of deriving the constants of nature from first principles and replaces it with a statistical argument over an ensemble of universes, most of which are inaccessible to observation. Others have suggested that the vacuum energy is not constant, but is dynamically adjusted by a field, sometimes called quintessence, which slowly evolves over cosmic time, driving the accelerated expansion without requiring a cosmological constant. In these models, the current acceleration is a transient phenomenon, and the vacuum energy will continue to change in the future, potentially affecting the ultimate fate of the universe. If the quintessence field interacts with the Higgs field, then measurements at CERN could provide clues about its properties, linking the physics of the very small to the cosmology of the very large. Yet another approach to the cosmological constant problem involves modifying gravity itself. General relativity has been tested extensively in the solar system and in binary pulsar systems, whereas predictions match observations with remarkable precision. But these tests probe gravity at relatively modest curvatures and over relatively short distances. On cosmological scales, the curvature is much smaller and the distances are much larger, and it is possible that general relativity breaks down, requiring modifications that have not yet been detected. Some modified gravity theories introduce additional fields or alter the relationship between curvature and energy density in ways that eliminate or reduce the need for a cosmological constant. These theories must be carefully constructed to avoid conflicting with solar system tests and other observations. But several viable candidates exist, and they make predictions that can be tested through cosmological observations. The anomaly at CERN, if it is real, might be connected to these cosmological puzzles. The Higgs field is unique among the fields of the Standard Model in that it has a non-zero vacuum expectation value, meaning that even in empty space, the field is not zero. This is what breaks the electroweak symmetry and gives mass to particles. But the value of this expectation value, about 246 gigaelectronvolts, is not explained by the theory. It is a parameter that must be input. Why does the Higgs field settle at this particular value rather than some other value, or zero? The shape of the Higgs potential determines where the minima are, but the shape itself is determined by the parameters of the theory, the mass term and the quartic coupling, which are also not derived but measured. If the Higgs sector is more complicated, if there are additional fields or interactions, then the effective potential at low energies could have features that are not apparent in the minimal model, and those features could manifest as anomalies in decay rates or production cross-sections. The connection between particle physics and cosmology runs deeper still. The conditions in the early universe, when it was hot and dense, were similar to the conditions created in particle colliders, but extended over vast volumes and long times. The processes that occurred in the early universe, the formation of matter, the generation of the matter-antimatter asymmetry, the production of dark matter, the evolution of the Higgs field, all depend on the particle content and interactions described by the Standard Model and its extensions. By studying high-energy collisions in the laboratory, physicists are effectively recreating and studying the early universe, probing the mechanisms that set the initial conditions for everything that followed. If the Standard Model is incomplete, if there are additional particles or forces that were active in the early universe, then understanding those extensions is essential for understanding how the universe came to have the properties it does. One of the most critical unsolved problems in cosmology is the origin of the matter-antimatter asymmetry. According to the Standard Model, matter and antimatter should have been produced in equal quantities in the Big Bang. As the universe cooled, matter and antimatter particles would have annihilated each other, leaving behind only radiation. Yet we observe a universe filled with matter, with very little antimatter. This implies that there was a slight excess of matter over antimatter in the early universe, an asymmetry of about 1 part in a billion. This tiny excess, after annihilation, constitutes all the matter we see today. The Standard Model contains the ingredients necessary for generating such an asymmetry, formulated in the Sakharov conditions: baryon number violation, C and CP violation, and departure from thermal equilibrium. However, the amount of CP violation in the Standard Model, which arises from the complex phase in the quark mixing matrix, is insufficient to account for the observed asymmetry. Additional sources of CP violation are needed, and these would likely be associated with new particles or interactions beyond the Standard Model. The anomaly at CERN involves particles, bottom quarks, and tau leptons that are sensitive to CP violation. If the anomaly is due to new physics, that new physics might also provide additional sources of CP violation, helping to explain the matter-antimatter asymmetry. Several models have been proposed along these lines, introducing new heavy particles that violate CP and interact preferentially with the third generation of fermions, the generation that includes the top and bottom quarks and the tau lepton. These models predict specific patterns of CP violation in the decays of B mesons, particles containing bottom quarks, and in the decays of tau leptons, and experiments at CERN and other facilities are actively searching for such patterns. Another cosmological puzzle is the nature of dark matter. Multiple lines of evidence, from the rotation curves of galaxies to the distribution of matter on large scales to the fluctuations in the cosmic microwave background, indicate that the vast majority of matter in the universe does not emit or absorb light and interacts with ordinary matter only through gravity. This dark matter is not accounted for by the Standard Model. None of the known particles have the right properties to be dark matter. It must be something new, and physicists have proposed a variety of candidates. Weakly interacting massive particles, or WIMPs, are perhaps the most studied. These are hypothetical particles with masses in the range of gigaelectronvolts to teraelectronvolts, similar to the masses of the W and Z bosons, and with interaction strengths comparable to the weak force. WIMPs arise naturally in supersymmetric extensions of the Standard Model, where the lightest supersymmetric particle is stable and could constitute dark matter. Despite extensive searches, WIMPs have not been detected, either in direct detection experiments that look for the recoil of atomic nuclei when struck by dark matter particles, or in indirect detection experiments that search the products of dark matter annihilation in space, or in collider experiments that attempt to produce dark matter particles in high-energy collisions. The non-detection has led to increasing interest in alternative dark matter candidates, including axions, very light particles that arise in solutions to the strong CP problem, and sterile neutrinos, hypothetical particles that interact even more weakly than ordinary neutrinos. The anomaly at CERN might be related to dark matter if the decays involve particles that escape the detector without interacting, carrying away energy and momentum in a way that mimics the signatures of other processes. This is difficult to distinguish from backgrounds, but with careful analysis, certain patterns can be identified. The strong CP problem is yet another mystery of the Standard Model. Quantum chromodynamics, the theory of the strong force, allows for determinate equations that would violate CP symmetry, leading to observable effects such as an electric dipole moment for the neutron. Experimenters searched for this dipole moment and found no evidence for it, constraining the coefficient of the CP violating term to be extraordinarily small, less than 1 part in a billion. There is no explanation within the standard model for why this coefficient, known as theta, should be so small. It is a fine-tuning problem similar to the cosmological constant problem. The most elegant solution proposed is the Peccei-Quinn mechanism, which introduces a new global symmetry that is spontaneously broken, leading to a dynamical relaxation of theta to 0. The breaking of this symmetry also predicts the existence of a new particle, the axion, which has properties that make it a candidate for dark matter. Axions, if they exist, are very light, with masses potentially many orders of magnitude smaller than the electron, and they interact very weakly with ordinary matter. Detecting them requires specialized experiments that exploit the fact that axions can convert into photons in the presence of a strong magnetic field. Several experiments are currently underway, using resonant cavities or telescopes to search for these conversions. If axions are discovered, it would solve 2 major problems at once, the strong CP problem and the dark matter problem, and it will provide further evidence that the standard model is incomplete. The anomaly at CERN is unlikely to be directly related to axions, because their interactions are too weak to produce observable effects in high-energy collisions. But if the new physics that explains the anomaly is part of a broader structure that also includes the Peccei-Quinn mechanism, then the two could be indirectly connected. The exploration of these connections requires a synthesis of particle physics, cosmology, astrophysics, and even condensed matter physics, because the mathematical techniques and physical intuitions developed in one area often find application in others. The concept of spontaneous symmetry breaking, for example, was developed in condensed matter physics to describe phase transitions in materials such as superconductors and magnets, and was later imported into particle physics to explain the Higgs mechanism. The methods of quantum field theory, originally developed to describe particles and forces, are now used to study critical phenomena in statistical mechanics, black hole thermodynamics, and even aspects of quantum information theory. This cross-fertilization is one of the strengths of theoretical physics, allowing ideas to migrate and mutate, finding new applications and generating new insights. The anomaly at CERN, whatever its ultimate explanation, is a reminder that nature is under no obligation to conform to our expectations, and that the boundaries of our knowledge are permeable and contingent. The standard model has been so successful for so long that it is easy to forget how strange it is, how many features it contains that seem arbitrary or ad hoc. Why are there 3 generations of fermions, nearly identical except for their masses? Why do the quarks mix in the particular pattern described by the CKM matrix? Why is the Higgs mass at 125 gigaelectronvolts rather than some other value? These questions do not have answers within the standard model. They are inputs, not predictions. A truly fundamental theory should explain them, deriving the structure of matter and forces from a smaller set of principles, or, ideally, from a single principle. String theory claims to be such a theory, deriving all particles and forces from the vibrations of strings and the geometry of the extra dimensions. But the theory has not yet been formulated in a complete, non-perturbative way, and its connection to the real world remains tentative. Loop quantum gravity offers a different path, focusing on the quantum structure of space-time, but has not yet demonstrated that it can recover general relativity in the appropriate limit, let alone make predictions for particle physics. Other approaches, such as causal set theory, asymptotic safety, and various forms of emergent gravity, are being explored, each with its own strengths and challenges. The field is in a state of flux, with no clear consensus on the way forward. Against this backdrop, the experimental results from CERN take on heightened significance. If the anomaly is confirmed, if it persists with more data and survives scrutiny, it will provide a concrete target for theoretical efforts, a phenomenon that must be explained. This is how progress is made. Theories are constructed to explain observations, and observations test theories. The interplay between the two drives the evolution of knowledge, revealing new layers of structure, new regularities, new questions. The anomaly, if it is real, is not an endpoint but beginning, the opening of a new chapter in the exploration of fundamental reality. To appreciate the scale of the undertaking, consider the complexity of the Large Hadron Collider itself. The machine accelerates protons, the nuclei of hydrogen atoms, to within a fraction of a percent of the speed of light, and then collides them head-on. The energy of the collision is converted into mass via Einstein's equation E equals mc squared, creating a spray of particles that fly outward in all directions. These particles are detected by layers of sensors arranged in cylindrical structures around the collision point. The innermost layers are silicon pixel detectors, arrays of tiny sensors that record the precise positions where charged particles pass through, allowing their trajectories to be reconstructed with micrometer precision. Farther out are calorimeters, devices that absorb the energy of particles, measuring how much energy each particle carries. The outermost layers are muon detectors because muons, heavy cousins of the electron, penetrate through the calorimeters and reach the outer regions. By combining the information from all these layers, physicists can identify the type of each particle, measure its energy and momentum, and infer the properties of the original collision. The data volume is staggering. At full luminosity, the LHC produces collisions at a rate of about 1 billion per second. Each collision generates hundreds or thousands of particles, and each particle leaves signals in dozens of detectors. Recording all this information is impossible. So the experiments use a triggering system, a multi-stage filter that decides in real time which collisions are interesting and should be saved and which can be discarded. The trigger must make this decision in microseconds, based on partial information, and it must be highly efficient, retaining the rare events that might signal new physics while rejecting the overwhelming background of ordinary collisions. Even after triggering, the data rate is enormous, on the order of petabytes per year, requiring large-scale computing infrastructure to store, process, and analyze. The analysis itself is a monumental task. Each event must be reconstructed, determining which signals correspond to which particles, disentangling overlapping events that occur when multiple collisions happen simultaneously, correcting for detector inefficiencies and mismeasurements. Once the events are reconstructed, they must be categorized, selecting those that match the signatures of interest. For the anomaly involving bottom quarks and tau leptons, this means identifying events where a bottom quark-antiquark pair is produced along with a tau lepton pair, and measuring the rate at which this occurs. The challenge is to distinguish these signal events from backgrounds, other processes that produce similar signatures but are not related to the phenomenon of interest. The backgrounds are typically much more numerous than the signal, and sophisticated statistical methods are required to extract the signal from the noise. These methods involve constructing probability distributions, models that describe how signal and background events are distributed in various observable quantities, such as energy, momentum, and angular distributions. By comparing the observed distributions to the expected distributions, one can infer whether there is an excess of signal events beyond what the background alone would produce. The strength of the excess is quantified by the statistical significance, typically measured in standard deviations. A 3 sigma excess means that the probability of observing such an excess by chance, if there is no signal, is about 1 in 1,000. A 5 sigma excess corresponds to a probability of less than 1 in a million, which is a threshold typically required to claim a discovery. The anomaly at CERN is currently at the 3 to 4 sigma level, significant but not yet definitive. One of the complications in interpreting the anomaly is the look elsewhere effect. When one searches for a signal, one does not know in advance exactly where it will appear. One must search over many possible masses, many possible decay channels, many possible regions of phase space. Each search represents an independent opportunity for a statistical fluctuation to occur, and if one performs enough searches, one is likely to find a fluctuation somewhere, even if there is no real signal. The look elsewhere effect quantifies this, adjusting the statistical significance to account for the number of independent searches performed. For the CERN anomaly, this adjustment is not trivial because the excess appears in multiple related channels, which are not fully independent. The detailed calculation requires careful consideration of the correlations between channels, and different statistical methods can give somewhat different results. Despite these subtleties, the anomaly has generated widespread interest because it is exactly the kind of signal that theorists have been hoping to find. The standard model is consistent with all measurements to date, but it is known to be incomplete, and the search for deviations is the primary goal of the experimental program. The fact that an excess has appeared in a theoretically motivated channel, involving particles that are sensitive to new physics, makes it particularly compelling. Moreover, The excess has persisted over multiple years of data taking, which reduces the likelihood that it is a statistical fluctuation. Fluctuations tend to wash out with more data, while real signals grow in significance. The fact that the anomaly has not washed out is encouraging, though not conclusive. The next steps are clear. More data is needed. The LHC is scheduled to run at higher luminosity in the coming years, producing more collisions and allowing for more precise measurements. Upgrades to the detectors are also planned, improving their ability to identify and measure particles. With more data and better detectors, the statistical significance of the anomaly will increase if it is real, or it will decrease if it is a fluctuation. In parallel, theorists will continue to refine their models, making more precise predictions and identifying new tests that can distinguish between different interpretations. The interplay between experiment and theory will continue, iterating toward a deeper understanding of whatever is causing the anomaly. But beyond the specific details of this particular anomaly, there is a broader question at stake. What is the nature of fundamental reality? What are the ultimate constituents of matter and energy? And what are the laws that govern their behavior? These questions have driven scientific inquiry for centuries, and each era has provided answers that seem final at the time, only to be revealed as approximations or special cases of deeper theories. The ancient Greeks proposed that matter was made of earth, air, fire, and water. Later, the atomic theory emerged, suggesting that matter is made of indivisible atoms. Then the atom was found to have internal structure, with a nucleus and electrons. Then the nucleus was found to be made of protons and neutrons. Then protons and neutrons were found to be made of quarks. At each stage, the picture became more detailed, more precise, and also more abstract, moving further from everyday experience into realms accessible only through sophisticated instruments and mathematical reasoning. The Standard Model represents the current stage of this progression, describing matter in terms of quantum fields, entities that permeate all of space and time, taking on different values at each point. Particles are excitations of these fields, localized ripples that propagate and interact according to the rules of quantum mechanics and relativity. This picture is both elegant and strange. It abandons the notion of particles as little billiard balls, replacing it with a picture where particles are better thought of as patterns and fields, and where the concept of position and trajectory becomes fuzzy, replaced by probability distributions. The mathematics is precise, but the physical interpretation is elusive, subject to debates that have continued since the early days of quantum mechanics. The measurement problem is one of the central interpretational puzzles. According to quantum mechanics, a system exists in a superposition of states until a measurement is made, at which point the superposition collapses into one definite outcome. But what constitutes a measurement? What distinguishes a measurement from any other interaction? Is a collapse a real physical process, or is it just a change in our knowledge? Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation, historically dominant, treats measurement as a primitive concept, not reducible to simpler terms. The many-worlds interpretation eliminates collapse, proposing that all possible outcomes occur, each in a different branch of a vast multiverse. The de Broglie-Bohm interpretation introduces hidden variables, additional degrees of freedom that determine the outcome of measurements in a deterministic way, restoring a kind of realism at the cost of non-locality. These interpretational debates have little practical impact on the predictions of quantum mechanics, which is why they are often dismissed as philosophical rather than scientific. But they become relevant when one tries to extend quantum mechanics to the entire universe, as is necessary in quantum cosmology. If the universe is a quantum system, and there are no external observers to perform measurements, what does it mean for the wave function to collapse? Does the many-worlds interpretation become necessary, or is there some other way to understand the emergence of classical reality from quantum substrates? These questions touch on deep issues about the nature of time, causality, and the relationship between observer and observed. Time is particularly problematic in quantum gravity. In general relativity, time is not absolute, but is part of the fabric of space-time, which is curved by matter and energy. Different observers can disagree about the duration between events, depending on their relative motion and their position in a gravitational field. In quantum mechanics, time is treated differently, as a parameter that labels the evolution of the wave function, external to the system rather than part of it. When one tries to combine the two, to quantize gravity, the role of time becomes unclear. In some approaches, such as the Wheeler-DeWitt equation, time disappears entirely at the fundamental level and must somehow emerge in the quantum state of the universe. This is known as the problem of time, and it remains unsolved. The emergence of time, and more generally the emergence of classical behavior from quantum substrates, is related to the phenomenon of decoherence. When a quantum system interacts with its environment, the superpositions that characterize quantum behavior become entangled with the environment, and if the environment is large and complex, the coherence between different branches of the superposition is lost on extremely short timescales. To an observer who does not have access to the environment, the system appears to be in one definite state, even though the full quantum description still involves a superposition. Decoherence does not solve the measurement problem, because it does not explain why one particular outcome is observed rather than another, but it does explain why we do not see macroscopic superpositions in everyday life, why Schrodinger's cat is either alive or dead, not both. The implications of decoherence for the interpretation of quantum mechanics are still being explored. Some argue that decoherence supports the many worlds interpretation, because it shows how the universe naturally splits into branches that do not interfere with each other. Others argue that decoherence is compatible with collapse interpretations, because the loss of coherence could be the physical mechanism that triggers collapse. Still others argue that decoherence is neutral with respect to interpretation, explaining the appearance of classical behavior without committing to any particular ontology. The debate continues, and it is unlikely to be resolved by experiment alone, because the different interpretations make the same predictions for all practical purposes. The choice between them is guided by philosophical considerations, by what one considers to be the most natural or elegant or conceptually satisfying picture of reality. The anomaly at CERN does not directly address these interpretational issues, but it does probe the boundary between the quantum and the classical, between the regime where quantum effects dominate and the regime where classical descriptions are adequate. At the energies and scales involved in collider experiments, quantum mechanics is essential. Particles are not following definite trajectories, but are described by wave functions, and the outcomes of collisions are probabilistic. The predictions of the Standard Model are quantum mechanical predictions, calculated using the formalism of quantum field theory, and the fact that these predictions match observations is a triumph of quantum mechanics. If the anomaly signals new physics, that new physics will also be quantum mechanical, involving new fields or new interactions described by quantum rules. But there is a sense in which the anomaly, if it is real, points towards something beyond the standard quantum field theory framework. Quantum field theory assumes that space-time is a fixed background, a stage on which the fields evolve. This assumption is valid when the curvature of space-time is small, as it is in a laboratory and in most astrophysical contexts. But in the early universe, near the Big Bang or near the singularities inside black holes, the curvature becomes large, and the back reaction of matter on space-time can no longer be neglected. In these regimes, one needs a theory of quantum gravity, a framework that treats space-time itself as a quantum entity. The anomaly at CERN occurs at energies far below the Planck scale, so quantum gravitational effects should be negligible. But if there are additional structures in the vacuum, or the Higgs sector is more complex than expected, those structures could be relics of quantum gravitational physics, imprints left over from the Planck era that persist in the low-energy world. This brings us back to the question of vacuum structure. In quantum field theory, the vacuum is not unique. There can be multiple vacua, different configurations of the fields that minimize the energy, and a universe could find itself in one or another depending on its history. In some scenarios, the universe underwent a series of phase transitions in its early history, each transition changing the vacuum state, breaking symmetries, and altering the effective laws of physics. The electroweak phase transition, when the Higgs field acquired its non-zero value, is one such transition. There may have been others at higher energies, associated with the unification of forces or with the breaking of additional symmetries. Each transition leaves signatures, not necessarily in the form of new particles that persist at present, but in the form of defects, topological features in the field configurations, or in correlations in the distribution of matter and energy. Cosmic strings are one example of such defects. If a symmetry is broken during a phase transition, and if the symmetry group has a non-trivial topology, then one-dimensional defects, strings can form stretching across the universe. These strings carry energy and produce gravitational effects, potentially detectable through their influence on the cosmic microwave background or through gravitational lensing. Searches for cosmic strings have so far yielded no detections, placing constraints on the energy scales and symmetries involved in early universe phase transitions. But the absence of detection does not rule out their existence. It merely constrains their properties, requiring that they be either very light or very rare, or that the phase transition that produce them occur at energies below current observational thresholds. Domain walls and monopoles are other types of topological defects that can form during phase transitions. Domain walls are two-dimensional surfaces separating regions where a field takes different values. Monopoles are point-like defects, analogous to isolated magnetic poles, which cannot exist in ordinary electromagnetism, but can arise in theories where the electromagnetic U1 symmetry is embedded in a larger gauge group that is broken at high energies. The overproduction of monopoles in the early universe is actually a problem for many grand unified theories, because if monopoles were as abundant as these theories predict, they would dominate the mass density of the universe, conflicting with observations. This is one of the motivations for inflationary cosmology, which proposes a period of exponential expansion in the very early universe that dilutes the density of monopoles and other defects to undetectable levels. Inflation is itself a profound modification of the standard Big Bang picture. In the standard picture, the universe began in a hot, dense state and has been expanding and cooling ever since. But this picture has problems. One is the horizon problem. Distant regions of the universe that have never been in causal contact have nearly identical properties, such as temperature, which seems to require some mechanism to coordinate them. Another is the flatness problem. The spatial curvature of the universe is observed to be very close to zero, which requires an extraordinary fine-tuning of the initial conditions unless there is some mechanism that drives the curvature toward zero. Inflation solves both problems by positing that the early universe underwent a brief period of extremely rapid expansion, driven by the energy density of a field, the inflaton, which was stuck in a temporary state far from its minimum energy. During inflation, the universe expanded by many orders of magnitude, smoothing out inhomogeneities and flattening the curvature. When the inflaton finally decayed, it released its energy into particles, reheating the universe and beginning the standard hot Big Bang evolution. The predictions of inflation have been tested through observations of the cosmic microwave background. The small fluctuations in the temperature of the CMB, at the level of 1 part in 100,000, are believed to be the result of quantum fluctuations in the inflaton field, stretched to cosmological scales by the expansion during inflation. The statistical properties of these fluctuations, their spectrum, and their non-Gaussianity depend on the details of the inflaton potential and the dynamics of inflation. So far, the observations are consistent with the simplest inflationary models, but they do not uniquely determine the model. Many different inflationary scenarios can fit the data, and distinguishing between them requires more precise measurements, particularly the polarization of the CMB and of the spectrum of gravitational waves produced during inflation. The inflaton is another example of a scalar field with a non-zero vacuum expectation value. Similar to the Higgs field, the fact that both the Higgs and the inflaton are scalars, and both play crucial roles in determining the structure of the universe, suggests a possible connection, but the details are unclear. Some models attempt to identify the Higgs with the inflaton, using the same field to drive inflation and to break the electroweak symmetry. These Higgs inflation models require carefully chosen couplings and a non-minimal coupling to gravity, meaning that the Higgs field interacts with the curvature of space-time in a way that is not present in the standard model. The viability of these models depends on the values of parameters, and the measured mass of the Higgs places constraints on the allowed parameter space. The anomaly at CERN, if it signals new physics in the Higgs sector, could affect these constraints, either opening up new regions of parameter space or closing off certain Higgs inflation scenarios. The connection between the Higgs and cosmology extends beyond inflation. The Higgs field also plays a role in baryogenesis, the process that generated the matter-antimatter asymmetry. One mechanism, known as electroweak baryogenesis, relies on the dynamics of the electroweak phase transition. If the transition was first order, meaning it proceeded through the nucleation of bubbles rather than occurring uniformly throughout space, then the bubble walls sweeping to the plasma could create the out-of-equilibrium conditions necessary for baryogenesis. The interactions of particles with the bubble walls, in the presence of CP violation, could lead to different production rates for baryons and antibaryons, generating a net baryon asymmetry. However, for this mechanism to work, the phase transition must be strongly first order, and the amount of CP violation must be sufficient. In the minimal standard model, the phase transition is not strongly first order, and the CP violation is insufficient. But if there are additional Higgs bosons or other new particles, the dynamics of the transition could be different, potentially allowing electroweak baryogenesis to succeed. The exploration of these possibilities requires a combination of collider experiments, cosmological observations, and theoretical modeling. Each provides a different window into the underlying physics, and the synthesis of information from all three is essential for constructing a coherent picture. The anomaly at CERN is one piece of this puzzle. By itself, it does not solve any of the major mysteries, but provides a clue, a hint that the standard model is not the end of the story, that there are additional structures waiting to be uncovered. If the anomaly persists and is eventually explained, it will open new avenues of inquiry, leading to new experiments, new theories, and new questions. One of the challenges in interpreting any new signal is to avoid confirmation bias, the tendency to see what one expects to see. The history of science is filled with examples of results that were initially hailed as breakthroughs, but later turned out to be errors or misinterpretations. The discovery of faster-than-light neutrinos in 2011, announced by the Opera collaboration, generated immense excitement because it would have overturned special relativity. But after extensive checks, the result was traced to a faulty cable connection, and the anomaly disappeared. The detection of the BICEP2 signal in 2014, initially interpreted as evidence of primordial gravitational waves from inflation, was later shown to be contaminated by dust emission from our own galaxy. These cautionary tales underscore the importance of rigorous verification, independent replication, and skepticism. The CERN collaborations are acutely aware of these dangers and have implemented multiple safeguards. The analyses are performed independently by different teams using different methods, and the results are compared to ensure consistency. Systematic uncertainties are carefully evaluated, and alternative explanations are considered. The data is scrutinized for signs of detector malfunctions, calibration errors, or analysis bugs. Only after all these checks are passed, and the result is robust, is it made public. The current anomaly has undergone the scrutiny, and it has survived, but it is still preliminary. The definitive test will come with more data, which is being collected continuously as the LHC continues to operate. In parallel with the experimental efforts, the theoretical community is working to understand the implications of the anomaly, developing models that can explain it, and making predictions for other observables that can be tested. This is a collaborative and competitive process, with hundreds of researchers around the world contributing ideas, calculations, and critiques. Some models are ruled out almost immediately because they conflict with existing data or make predictions that are obviously wrong. Others survive longer, pass the initial tests in generating interest, but eventually run into problems as more detailed calculations are performed. A few models may turn out to be viable, consistent with all available data, and making distinctive predictions that can be tested in future experiments. The selection among these viable models will depend on which predictions are confirmed and which are ruled out, a process that can take years or decades. The anomaly also has implications for the future of particle physics. For many years, the field has been anticipating construction of a next-generation collider more powerful than the LHC, capable of reaching higher energies and producing rarer processes. Several designs have been proposed, including the future circular collider at CERN, which would be a 100-kilometer ring colliding protons at energies up to 100 teraelectronvolts, and the International Linear Collider, which would collide electrons and positrons at energies up to 1 teraelectronvolts with extremely high precision. These machines are enormously expensive, costing tens of billions of dollars, and require international collaboration and long-term commitment. The decision to build them depends in part on the scientific case, on whether there are clear targets to study and clear questions to answer. The anomaly at CERN strengthens the case for a next-generation collider. If it is confirmed and explained by new physics at accessible energy scales, then a more powerful machine could produce the new particles directly, studying their properties in detail and mapping out the structure of the extended theory. Even if the anomaly turns out to be a fluctuation, the precision measurements that a next-generation collider could make will provide powerful constraints on possible extensions of the standard model, narrowing the range of viable theories and guiding theoretical development. The alternative, not building a next-generation collider, would leave many questions unanswered and would shift the focus of particle physics toward astrophysical and cosmological observations, which probe different aspects of fundamental physics, but do not provide the same level of control and precision as laboratory experiments. The interplay between laboratory experiments and astrophysical observations is itself an important feature of modern physics. Astrophysical systems provide natural laboratories where extreme conditions, impossible to recreate on Earth, occur naturally. Black holes, neutron stars, supernovae, and the early universe all involve energies, densities, and gravitational fields far beyond anything achievable in a laboratory. Observations of these systems can test general relativity in strong field regimes, probe the properties of matter at nuclear densities and beyond, study the formation and evolution of structure in the universe, and search for rare processes or exotic particles that are too weakly interacting to detect directly. The detection of gravitational wave by LIGO and Virgo has opened a new window on these phenomena, allowing the direct observation of black hole mergers and neutron star collisions, events that produce signals carrying information about the properties of space-time and matter under extreme conditions. The mergers of neutron stars are particularly interesting for particle physics because they produce conditions where the density of matter exceeds that of atomic nuclei, entering a regime where the equation of state, the relationship between pressure and density, is not well understood. Neutron stars are supported against gravitational collapse by the degeneracy pressure of neutrons, a quantum mechanical effect that arises because neutrons are fermions and cannot occupy the same quantum state. But at higher densities, other effects come into play. Neutrons can be converted into hyperons, strange baryons that contain strange quarks. At even higher densities, the quarks themselves might become deconfined, forming a quark-gluon plasma similar to the state produced in heavy ion collisions at CERN. The phase transition from hadronic matter to quark matter, if it occurs, would affect the structure of neutron stars, changing their radius, their maximum mass, and the gravitational wave signals they produce when they merge. By observing neutron star mergers with gravitational wave detectors and with electromagnetic telescopes, and by comparing the observations to theoretical models, physicists can learn about the equation of state and the phase structure of dense matter, complementing the information obtained from collider experiments. The production of heavy elements in the universe is another area where astrophysics and particle physics intersect. Elements heavier than iron cannot be produced efficiently in normal stellar burning because the fusion of iron and heavier nuclei consumes energy rather than releasing it. Instead, these elements are produced in explosive events, such as supernovae and neutron star mergers, through rapid neutron capture processes. During these events, atomic nuclei capture neutrons at rates faster than they can decay, building up heavy elements through a chain of neutron captures and beta decays. The details of this process depend on the nuclear physics of neutron-rich isotopes, many of which are unstable and have not been studied in the laboratory. Experiments at radioactive beam facilities are working to measure the properties of these isotopes, providing the nuclear physics input needed to model the production of heavy elements and to understand the chemical evolution of a universe. The connection to the anomaly at CERN is indirect but real. The production of neutron-rich isotopes and the equation of state of dense matter both depend on the properties of the strong force at low energies, the regime of quantum chromodynamics, where the coupling is large and perturbative calculations break down. Understanding QCD in this regime requires non-perturbative methods, such as lattice QCD, where the equations are solved numerically on a discretized space-time grid. Lattice QCD has made tremendous progress in recent decades, calculating the masses of hadrons, the spectrum of excited states, and the properties of the QCD phase transition with increasing precision. But it is computationally intensive, requiring supercomputers and sophisticated algorithms, and there are still many open questions. The anomaly at CERN, if it involves modifications to the Higgs sector, could affect the running of the QCD coupling, the way its strength changes with energy, and this could have subtle effects on low-energy QCD observables. By combining collider data, lattice QCD calculations, and astrophysical observations, It may be possible to disentangle these effects and gain a more complete understanding of the strong force. Another frontier where particle physics and astrophysics meet is in the study of cosmic rays, high-energy particles that bombard the Earth from space. Cosmic rays include protons, nuclei, electrons, and photons, with energies ranging from millions of electron volts up to more than 10 to the 20th electron volts, the highest energy particles ever observed. The sources of the highest energy cosmic rays are unknown. They could be produced in the vicinity of supermassive black holes, in the jets of active galactic nuclei, in the shocks of supernova remnants, or in more exotic processes involving dark matter or topological defects. Understanding the sources requires understanding the propagation of cosmic rays through the galaxy and the intergalactic medium, which is complicated by the presence of magnetic fields that deflect the charged particles, obscuring their origins. Photons and neutrinos, being neutral, point back to their sources, and multi-messenger astronomy, combining observations of photons, neutrinos, and gravitational waves, is beginning to unravel the mysteries of the most energetic events in the universe. The detection of high-energy neutrinos by the IceCube Observatory has provided tantalizing hints about the sources of cosmic rays. Neutrinos are produced when cosmic ray protons collide with ambient matter or radiation, creating pions that decay into neutrinos and photons. By detecting neutrinos and tracing them back to their sources, one can identify the sites where cosmic ray acceleration is occurring. IceCube has detected neutrinos coming from the direction of active galactic nuclei and from other sources, but the picture is not yet complete. More detections are needed, and next-generation neutrino telescopes, such as KM3NeT and IceCube Gen 2, are being planned to increase the detection rate and improve the angular resolution. The interplay between cosmic ray physics and collider physics is bidirectional. Collider experiments provide data on particle interactions at high energies, which is essential for modeling the propagation and interactions of cosmic rays. Conversely, cosmic ray observations provide information about particle physics at energies far above what colliders can achieve. The highest energy cosmic rays have energies more than 1,000,000 times higher than the LHC, probing scales where new physics might become manifest. If there are violations of Lorentz invariance, or if there are new interactions or particles at ultra-high energies, cosmic rays could reveal them. The challenge is that cosmic rays arrive at low rates, and the interactions occur in the atmosphere or in detected materials, making the measurements indirect and subject to large uncertainties. Nevertheless, cosmic ray physics provides a complementary approach to particle physics, extending the reach of experimental investigations beyond what is possible in the laboratory. The anomaly at CERN, if it is related to new physics, might also have signatures in cosmic rays. If the new particles can be produced in high-energy collisions, they might be produced in interactions of cosmic ray protons with the atmosphere, and their decay products might be detectable. Alternatively, if the new physics involves modifications to the Higgs sector or the vacuum, it might affect the propagation of cosmic rays through space, altering the predicted fluxes or energy spectra. These effects are likely to be small, but with the large data sets now available from cosmic ray observatories, even small effects can be detected if one knows what to look for. The search for new physics is thus a multi-front endeavor involving collider experiments, astrophysical observations, cosmological surveys, and precision measurements of fundamental constants. Each approach has its strengths and weaknesses, and the combination provides a more complete picture than any single method could achieve. The anomaly at CERN is one data point in this larger effort, a signal that stands out against the background and demands explanation. Whether it leads to a major discovery or fades into statistical noise, it is a reminder of the value of exploration, of pushing the boundaries of knowledge, of asking questions even when the answers are uncertain. The philosophical implications of this endeavor are profound. The quest to understand the fundamental structure of reality is driven by curiosity, by the desire to know why things are the way they are, but also touches on questions about the nature of explanation, the limits of knowledge, and the relationship between mathematics and physical reality. Why is the universe comprehensible at all? Why do mathematical equations describe the behavior of physical systems with such precision? These are questions that physics itself cannot answer, because they lie at the boundary between science and philosophy. But they are questions that physicists inevitably confront as they probe deeper into the workings of nature. the effectiveness of mathematics in physics, famously discussed by Eugene Wigner in his essay on the unreasonable effectiveness of mathematics in the natural sciences, is a recurring source of wonder. Mathematics is a human invention, a formal system of symbols and rules developed for its own internal coherence and beauty. Yet this abstract system turns out to describe the physical world with extraordinary accuracy, not only capturing the patterns we observe, but predicting new phenomena that were later confirmed. This could be a coincidence, or it could indicate something deeper, a fundamental connection between mathematical structure and physical existence. Some physicists and philosophers have argued for a Platonic view, in which mathematical objects exist independently of human minds, and physical objects are instantiations or shadows of these mathematical forms. Others argue for a more pragmatic view, in which mathematics is simply a tool refined over centuries to match the patterns we observe, and its effectiveness is a result of selection rather than revelation. The anomaly at CERN does not resolve this debate, but exemplifies a process by which the effectiveness of mathematics is tested. The Standard Model is a mathematical structure, a set of equations and symmetries, and its predictions are mathematical predictions, calculated using the formalism of quantum field theory. The fact that these predictions match observations is evidence that the mathematical structure captures something real about the physical world. If the anomaly signals a deviation from the Standard Model, it means that the mathematical structure is incomplete, that there are additional terms in equations or additional symmetries that have not yet been identified. The task then becomes one of discovering the right mathematical structure, the one that not only explains the anomaly but also fits with all other observations and perhaps simplifies or unifies our understanding. The search for simplicity and unification has been a guiding principle in physics since the time of Newton. The realization that the same gravitational force governs the motion of falling apples and orbiting planets was profound unification, showing that disparate phenomena could be explained by a single principle. Maxwell's unification of electricity and magnetism, showing that they are two aspects of a single electromagnetic force, was another milestone. Einstein's unification of space and time into space-time and his geometric interpretation of gravity extended this program further. The Standard Model itself is a unification, combining the electromagnetic and weak forces into the electroweak force, and incorporating the strong force within the same mathematical framework. The hope is that gravity can eventually be unified with the other forces, leading to a theory of everything, a single set of equations from which all physical phenomena can be derived. But the pursuit of unification has not been straightforward. Each unification has required new concepts, new mathematical structures, and often a willingness to abandon cherished assumptions. Special relativity required abandoning absolute time. General relativity required abandoning the notion of gravity as a force. Quantum mechanics required abandoning determinism and the classical concept of trajectories. Each of these revolutions was resisted initially because the new ideas seemed counterintuitive or philosophically problematic, but eventually they were accepted because they explained observations that the old theories could not. The lesson is that nature is under no obligation to conform to our intuitions, and that the path to deeper understanding often requires us to revise our most basic concepts. The anomaly at CERN could be the beginning of another such revision. If it signals new physics, it could require us to rethink the Higgs mechanism, or the structure of space-time, or the nature of the vacuum, or some other fundamental aspect of our current framework. The specifics will depend on what the new physics turns out to be. But the process of discovery and conceptual revision will likely follow the pattern established by previous revolutions. There will be initial confusion and controversy as different groups propose different interpretations and models. There will be theoretical developments as new mathematical structures are explored and new predictions are made. There will be experimental tests as those predictions are compared to observations. And eventually, a consensus will emerge, a new framework that incorporates the old successes while explaining the new. This process is not linear or deterministic. It involves false starts, dead ends, and serendipitous discoveries. It requires creativity, persistence, and collaboration across disciplines and generations. It is a fundamentally human endeavor, shaped by the limitations and strengths of human cognition, by the social structures of scientific communities, by the availability of funding and technology, and by the accident of history. Yet it is also a process that transcends individual humans, because the knowledge that is generated is cumulative and universal, accessible to anyone who learns the necessary background and engages with the evidence and arguments. The anomaly at CERN is a moment in this ongoing process, a point where the accumulated knowledge of decades meets the uncertainty of new observations, where theory and experiment intersect, and where the next steps are not yet clear. It is a moment filled with possibility, where the outcome could be a confirmation of existing ideas, or a radical departure into new territory, or something in between. The excitement comes not from knowing the answer, but from being at the edge of knowledge, where the questions are genuine and the stakes are high. As the data continues to accumulate, as the analyses are refined, and as the theoretical models are developed and tested, the picture will gradually come into focus. The anomaly will either strengthen, crossing the 5 sigma threshold and establishing itself as a definitive signal of new physics, or it will weaken, fading back into the statistical background and joining the long list of tantalizing hints that did not pan out. Either outcome is valuable. A confirmed signal would open new research directions, possibly leading to a more complete theory and a deeper understanding of reality. A no result would place powerful constraints on possible extensions of the standard model, narrowing the range of viable theories and guiding the focus of future efforts. In the meantime, the work continues. Collisions occur at the LHC every few nanoseconds, each one a miniature recreation of conditions that existed in the first moments after the Big Bang. Detectors record the debris, computers process the data, and physicists analyze the results, searching for patterns, testing hypotheses, and refining their understanding. It is painstaking work, requiring patience, precision, and a tolerance for ambiguity. Most collisions are unremarkable, producing outcomes that are well understood and expected. But occasionally, something unusual appears, a deviation from predictions, a hint that there is more to discover. The anomaly involving bottom quarks and tau leptons is one such hint, and has captured the attention of the community precisely because it suggests that the map of reality, as currently drawn, is incomplete. The incompleteness of the standard model has been known for decades, but the nature of the completion has remained elusive. The anomaly provides a concrete focus, a specific set of observations that any candidate theory must explain. This focus sharpens the theoretical effort, turning abstract speculation into testable science. Models that predict the right excess in the right channels, while remaining consistent with all other measurements, are taken seriously. Models that fail these tests are discarded. The ITER,